Hello everyone, this is Dr. Lennon, and today we're going to look at applications to economics. So we're going to look at the PowerPoint in this lecture, and then we'll do some more examples in the next. But basically we're going to be going over a few topics, consumer and producer surplus and future value. And the integral is going to allow us to compute all of those things in economics when we have curves that are modeling certain behavior. With consumer surplus, it's going to involve demand. With producer surplus, it's going to involve supply. And with future value, it's going to involve growth rates and income streams. So let's jump right in. So the first is consumer surplus. So basically, we're looking at a graph here. So if you've had economics, you know a typical demand curve is going to be something that's decreasing when you graph it. On the y-axis here, we have the price of the quantity, and on the x-axis we have the quantity that is being sold at the particular price. So as you can see, as the quantity increases, the demand goes down, right? When there's a larger amount being produced, then the price is going to be cheaper and there's going to be less demand. So our demand function is a decreasing quantity. And when we have that capital Q and capital P, that's talking about a very specific price point. So a lot of times we're going to be looking at particular intersections of graphs using either horizontal lines or supply curves. So again, we've just got our function there. So you really have to be a little bit careful here whether they're using capital P or lowercase p or capital Q or lowercase q. Capital P and a capital Q typically indicate a particular point, whereas the variables are denoted with a lowercase. So if you look at such a particular price point, you have some consumers who would be willing to pay more, and they benefit by not having to, right? They're essentially saving money. So the difference when the consumers that are willing to pay more and what they actually pay, that's good for the consumer, and that's known as the consumer surplus. So this can be found by essentially integrating. If you can picture a horizontal line intersecting this curve, the area between the curve and the horizontal line below it is going to form the consumer surplus. So we should see that in this next graph. And essentially, this is just looking at finding the area between two curves. If we're finding the area between two curves, we take the one on top, which is going to be demand, minus the thing below, which is price, which is going to be reflected by a horizontal line. And then our x values are going to be going from 0 to capital Q, which is the quantity corresponding to that capital P price. So let's have a look. Again, we have the graph there. So the consumer surplus is the shaded region. So again, the consumer surplus is found by integrating and then just subtracting the demand curve from the particular price point, capital P. So usually what's going to happen here is we're going to have some formula that's going to specify this demand, some decreasing function, and then we're just going to have to subtract some constant value from it and then do the integration. So in this particular example, we have a quadratic function, which is a part of a parabola that's shaped downward, and they want us to find the consumer surplus when the sales level is 500. So notice from the previous slide, what we have to do is we have to take this formula. So this capital P is really our demand curve, D of Q, 1200 minus 0.2Q minus 0.0001Q squared. So we're going to be integrating from 0 to 500, but we don't yet have the price point. So the first step to find the price point is to plug 500 in for Q above. Once we have that price point, that's going to give us the actual capital P value that we're going to need to subtract from the demand curve when we do the integration. So we're going to do 1200 minus 0.2 times 500 minus 0.0001 times 500 squared. That's going to give us capital P. So that's what we see below. And that comes out to 1075. So basically our setup for this is the consumer surplus is going to be the integral from 0 to 500. And we're going to have to take that 1200 minus 0.2Q minus 0.0001Q squared and then subtract this 1075. So that's exactly what we see here. So 1200 minus 1075 comes out to 125. So we can simplify the integrand. And then to integrate here, we're just using the polynomial rules. So the antiderivative of 125 is 125q, and then 0.2, we're going to make that q squared and divide by 2, and then the q squared, we're going to make that q cubed and divide by 3. So we get the antiderivative, we plug in the numbers. Again, whenever you plug 0 into the antiderivative of a polynomial, it just vanishes. And so we get our answer, which the consumer surplus here is $33,333.33. Okay, so the producer surplus is going to be kind of the dual notion. So rather than looking at a demand curve, we're going to be looking at a supply curve. So a supply curve is going to be an increasing function with respect to quantity. And then this is going to be the amount that the benefits the producer. So we're going to be looking at an area before, but this area is going to be below the curve. So as we see here, the supply function is going to be an increasing quantity, as we said. And if we go ahead and look, there's a typical graph. We see the same sort of thing. So now when we integrate, if we look at this particular price point, we can look at the horizontal line through capital P, and that will be above the curve from 0 to Q. So it would be doing the integral of that constant value minus whatever the formula is for our supply curve. So this is the producer surplus, and basically it's benefiting the producer because it's the goods that they can sell at more than its minimum acceptable price. So again, this is just determined using an integral. So it's really the same. You just have to remember that you're doing the constant minus the supply curve for this example. Okay, so this is just getting into the details of how we turn a Riemann sum into an integral. So we're going to kind of overlook those details for now and just go ahead and jump to the example. Here is the integration formula again. It's just the integral from 0 to Q of P minus the supply curve. And there's the picture that we kind of should have expected to see coming. So in this example, we have a manufacturer, and the supply is given by 5.4 plus 0.001 times Q to the 1.2. So we want to find the producer surplus when the clock sold is 2,000. So again, that's a Q value, so we're going to need to plug that in to find the price in order to subtract the supply curve from that. So plug 2,000 into S of Q up there, and we get 5.4 plus 0.001 times 2,000 raised to the 1.2. Punch that into your calculator, and you get an answer of about 14.55. So we're going to do 14.55 minus 5.4, and when you distribute it, it'll be minus 0.001 Q to the 1.2, and that's going to be integrated from 0 to 2,000. So that's exactly what we see here. Again, 14.55 minus 5.4 is going to come out to 9.51, or 9.15, excuse me. I mixed the order up in my head. Minus that 0.001 Q to the 1.2. And again, we're just using the polynomial rules here, so technically it's not a polynomial, it's Q to the 1.2. We're using the power rule, I should say. So the antiderivative of 9.15 is going to be 9.15Q, and to integrate Q to the 1.2, that will be Q to the 2.2, and then we're going to have to divide the entire term by 2.2. And then plug in our numbers. Again, plugging in 0 is going to make everything go away, so really we can just plug in 2,000 and then punch that into our calculator. So we get our answer of $9,985.36. Continuing onward, we should be moving along to... Okay, so we've got the producer surplus. All right, so now we're talking about total surplus. So you could look at the supply and demand curves, if you knew them, of a product at the same time, and you could find the point where they intersect. That's the so-called equilibrium point. You've probably heard that term in economics. And if you look at the area formed from the supply curve or the demand curve to the supply curve, from 0 to the equilibrium point, that is what's going to give the total surplus. And essentially, that's the same thing as looking at the producer surplus and the consumer surplus and adding them together. So you could do them separately, or you can do them all in one step. If you do them in one step, you're just doing D of Q minus S of Q and integrating from 0 to this capital Q at the point where they meet. Of course, for such a problem, they can just give you the demand curve and the supply curve, and then it would be up to you to find the point of intersection, which might require a little bit of algebra. So let's just keep that in mind. Okay, so we see such a thing here. We have a demand function, which is a exponential decay, and we have a supply function, which is exponential growth. Again, Q here is measured in thousands, and they want to know what price should they sell in order to maximize the total surplus. One thing to note is that the equilibrium point will be the point that maximizes that. I don't know if they said that in the previous page, but that is something you should know from economics. Probably you've heard that profit is maximized where supply meets demand or something like that. So what is the total surplus? Actually, profit is maximized when marginal cost equals marginal revenue. That's something we learned last semester in Calc 1. But the surplus is going to be maximized when the at the point where the demand is equal to the supply. So maybe I said that wrong the first time, but hopefully I've cleared that up now. Okay, so the first point, we need to find where they intersect. So we're going to set 14e to the negative 0.5q equal to 2e to the 0.12q. And so we can multiply by e to the 0.15q because remember, when two exponential quantities have the same base, you add their exponents. So on the left-hand side, when you add those two, you'll get e to the 0, which is just 1. So we'll be left with 7 on the left. And on the right, actually implicitly here, they did one step before multiplying by e to the 0.15. They divided both sides by 2. So when you divide the left side by 2, you're left with a 7. On the right side, you just have the exponential. Okay, and then adding the exponents on the right is going to leave us with e to the 0.27q. So we have 7 equals e to the 0.27q. Then to solve this, we can take the natural log of both sides. The right-hand side will just be left with 0.27q, which we can divide by the 0.27 to solve for q. So we start by taking the natural log, and then we divide by 0.27. So this gives us our quantity of about 7.2071. And again, what is that? Why was that important? Well, that's the quantity, so we need that to figure out where we're integrating from. So we're going to be integrating from 0 to this number, 7.21 or thereabouts. And then we also need to figure out, well, in this case, we don't actually need to know the price where they meet because we're just going to take the demand curve and subtract the supply curve. So it is not important for the total surplus to actually know the price of the equilibrium point. We can get away with just knowing the quantity. They plugged it in anyway, so we know, in fact, that the equilibrium price point is $4.75, although, as I mentioned, it's not completely crucial in finding the total surplus. So, again, we integrate from 0 to 7.2, subtract the curves, and then remember the integration rule for e to a constant times a variable. We just divide by whatever the constant is. So the first term will be dividing by negative 0.15, and the second term will be dividing by 0.12. And again, we're dealing with exponentials here, so when we plug in 0, the things do not go away, right? E to the 0 is going to end up being 1. So we do need to, in fact, plug in 0 and then subtract that quantity. So plug in the top number for Q, and then subtract when you plug in 0 for Q. And we'll see the numbers that we get there. Again, they've taken the liberty when they subtract. Really, there should be parentheses around the second two terms, but they've already distributed the negative. So we got so that's why we have the negative and the positive. So they've already done the distributing for us. Okay, so we get the total surplus. Again, Q was measured in thousands, so this is really $38,761. So that's the total surplus. Not too much different from doing a consumer surplus or a producer surplus. Okay, so income streams, really what we want to look at is just the future value here. So when we're talking about income streams, we're talking about something that might be changing, right? Oftentimes you might say, well, imagine you earn $50,000 for 10 years, blah, 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 blah. But usually that's not a realistic assessment of how things go. Oftentimes you're going to have some typical cost of living increase, or you could try to predict a raise or something like that. So you can have something that's a little bit more complicated. You could actually have a function predicting your income stream. So that's something we're going to talk about here. In the example they give, they say, imagine you have a business that earns an income, and then on top of that, you take that income and then you invest it and you're earning interest. So you can talk about that as well. So for these, we're typically going to be talking about the income earning stream, earning things continuously. So remember, there's two big differences when we talk about interest, but when you talk about continuous interest, you're just talking about e to some rate times time. So if you go back and look at your exponential formulas, typically continuous is going to be the form that involves the Euler's number e. Okay, so the amount of earnings is the future value of the investment. So let's go ahead. Again, they're talking here about the integral, how you get the integral from looking at the Riemann sums, where f of t is your income stream, and we're considering the input variable in terms of years. But here's essentially the formula that we're working with. This fv equals the integral from 0 to capital T of f of t times e to the r times the quantity capital T minus t. Now this is typically not the form that I use. We'll look at the form that we use in a second, because if you distribute that r on top, e to the r times capital T, r and capital T are both constants and your only variable is lowercase t. So really the common formula that we're going to use here is number 4. And you can see above they applied some algebra to demonstrate that these two formulas from the previous iteration 3 and 4 are actually equal. So they just distributed the r in the exponent, and then they used exponent rules to write that as e to the r times capital T times e to the negative lowercase r times t. And then e to the r times capital T is a constant, so they can just pull that out in front of the integral. So this is the typical future value formula that we're going to be using. So let's go ahead and look at this example, and then we'll call it a day, and we will look at some other problems in the next lecture. So Brad inherits a small apartment building that generates income at an estimated rate of $22,000 e to the 0.02 t dollars per year, t years from now. He invests the income in a bank account that earns 4.5% interest compounded continuously. What is the value of his income from the building after 6 years? So we have the income stream there, 22,000 times e to the 0.02 t, and then r from the formula is this 4.5%, so that's 0.045. And we're looking for the income after 6 years. So capital T is going to be 6 years. So we can pretty much see how we're going to set up our problem if we can figure out what f of t is. So f of t is the 22,000 times e to the 0.02 t. Lowercase r is 0.045. And capital T is 6. So once you know those three things, you just plug them into the future value formula and you are all set. So we plug those things in. 0.045 replaces lowercase r, 6 replaces capital T, and the 22,000 times e to the 0.02 t replaces f of t. Again, the e is the common base, so you can just add the exponents. So we can see inside the integral that's going to turn into e to the negative 0.025 t. And to integrate, you just write down the same exponential term and then divide by the e to the negative, or divide by the constant in the exponent, negative 0.025. So that's the antiderivative. Again, it's an exponential, so it is important to plug in 0 and actually subtract the terms. So we go ahead and do that. And we have our future value of $160,571. And that's it for computing the future value. So like I said, we'll finish here with the PowerPoint slide lecture. in the next one, I will come back and we'll actually do some more examples. But that is it for doing the intro to the applications to economics. So this is Dr. Lennon signing off.